Okay, so till last class we have looked at the MOSFET structure. We also looked at how the current and voltage curves look like. So today we will start looking at some of the circuits using MOSFETs. And so the first thing that we need to do is basically to see how a MOSFET is biased or how does it respond at DC. Okay. So let's take this circuit for example and let's try to evaluate it. So this will give us some better understanding. Okay. So this is RD, RS. This is minus 2.5 volt. This is grounded. Okay. Now for this problem, the required ID is 0.4 milliamp, okay, and VD, the drain voltage, is given as 0.5 volt plus 0.5 volt, okay. So you need to design the circuit. When we say design the circuit, we basically need to design the values of RD and RS such that we get this amount of current which is flowing. So the threshold voltage is given by 0.7 volt, and also mu n Cox product is given as 100 microamp per volt squared. Okay, the channel length is 1 micrometer, width is given by 32 micrometer. Okay, you can take channel length modulation, neglect the channel length modulation, or in other words, take lambda to be 0. Okay, so here we need to find RD and RS. Finding RD is very simple, right? You want VD to be at 0.5 volt. This has to be 0.5 volt. So the drop across this is 2 volt. So what is the value of RD? Yeah, this is 5 kilo ohm. Okay. Basically 2 volt divided by 0.4 milliamp, and you get it directly. Now how to find the value of RS? Okay. Now if it were a BJT circuit, we would just close our eyes and say the VBE is 0.7 nominally, and then we will proceed with the analysis. But whereas in MOSFET, the VGS is not going to take any kind of fixed value like BJT. Okay, the gate to source voltage is going to be much. It will vary all over the place depending on the the mu and Cox, the W over L ratio, and the current that is required. So you cannot assume that it is going to be nominally some voltage. You need to figure it out, or you need to design for it or analyze and get the answer. Okay, so basically this is assumed. So here you can see that here it is 0.5 volt, and you have some sufficient amount of voltage across the drain. So let's assume that it is going to be in the saturation region. Okay, so in the saturation region, the expression is something like this, right? Mu n Cox by 2 W over L VGS minus VTH the whole square. Okay, so from this you can calculate what is VGS required. What is the VGS required?
So is it 1.2 volts?
Correct. It is 1.2 volts, and so the gate to source voltage is 1.2 volt. I hope all of you were able to get it, right? So what it basically means that, since this is 0 volt, it needs 1.2 volt across the gate and the source, and therefore this node voltage is going to be at minus 1.2. Okay. Now we can cross check and verify if our assumption of saturation of the MOSFET is a valid assumption or not. So what is VDS? VDS is 0.5 minus of minus 1.2, which is 1.7 volt, which is definitely greater than 1.2 minus 0.7, which is 0.5 volt. So this is in saturation region. So you have to make sure that it is in the saturation region, because that is not always guaranteed. Okay. All right. Now finding the value of RS is simple. So what is the value of RS? Yeah.
So one thing, since we are using the equation of the saturation region itself, then won't we be expecting?
No, you will
even
not.
If we evaluate VDS.
No, you will not, because in this equation VDS is not there, right? There is no VDS in this equation, right? So what you are saying is, like, if it is in the saturation region, okay, this needs a gate to source voltage of so much. That's all. The VDS is not included in this equation. Now there will be some examples probably in the textbook also, and maybe some exercise assignments that I can give, where you will find that you start with an assumption of saturation region, and you'll find that somewhere it doesn't agree. Okay, the VDS will be lesser than that, and you will know that it is not a correct assumption.
Yes, sir.
Okay, so here in this equation, we are not even considering VDS. VDS is like an independent term as far as this. This is what is called as the square law equation. Okay. All right. So what is the value of RS? So the voltage across RS is nothing but you have what, 1.3 volt. Okay, and you have the same. So here, what, as we mentioned,
3 kilo.
It will be, is it 3 or 3 point something?
$3.25.
Yeah, 3.25 kilo. Okay. So the important thing here to note in MOSFETs is that the gate current Ig is 0 always. Okay, at least at low frequencies, the gate current is 0. Okay, so this is in stark contrast to the BJTs, where there is a finite amount of non-zero amount of base current. Okay, and because Ig is 0, you can always assume Id is equal to Is. This is one of the major differences between BJTs and MOSFETs, because although their structure and principle of operation and other things change, there are a lot of similarities, but there are also some very stark differences, and this is one of them. Okay, gate current is 0, and therefore always drain current and source current are equal. Okay, all right. So let's move on to another concept in MOSFETs, which is what is called as diode connected transistors. Now this is true for both BJTs and MOSFETs. So since I did not take it in BJT, I will include it here. So diode connected transistors. So let's start with a BJT. Okay. So if you take let's say an NPN transistor, right, and you short its base and collector. Okay. Now what happens? So this is an NPN device. So you have N, P, and N. Now you have shorted these two together, right? So right now it is basically a PN junction diode. Correct? You have this base region P, and you have the emitter region N. The base collector region is basically shorted out, and so any effect there is basically minimized, right? So this is why this is called as a diode connected transistor, okay, or diode connection of a transistor, okay. And so basically what happens is, now VCE is equal to VBE is equal to the nominal 0.7 volts, okay. So in essence this acts as a diode, that's it, all right. Now why do people do that? It's basically, if you recall, I mean, many of our circuits we saw that there is going to be a current source, and I don't know if I discussed how to implement a current source. So how do you implement a current source? So what is the property of a current source?
It should give no matter what voltage up drops across it.
Correct. So an ideal current source, right? If you plot the I versus the voltage, right? If you take a, let's say, current source, and this is going to be V and this is going to be I, right? So basically this is supposed to be constant, right? So I is independent of V. This is an ideal current source. And I think we have already discussed what happens in a real current source. Any real current source will have a shunt impedance, and therefore there will be a small amount of droop in the current, either an increase or decrease depending on the way in which you connect things and so on, right? So this is the definition of a current source, right? Now how can we build a current source? Of course, you have already done that in your lab, like using op amps and BJTs and so on. But in many cases, if you want a very cheap current source, okay, especially if you want to build the MOSFET, the op amp based current source that you built in lab last week. So that's a more, that's more precise in the sense that, like, especially if you want to have very good, very precise control over the current and so on, you can do things like that. Okay. Now, for example, when you have a common gate, right? A common base amplifier, and we said we are biasing it using a current source, right? Something like this. Now, for this current source, if you start putting op amps for each and everything, then it becomes more tedious. Okay. If you look at the BJTs or a MOSFET's output characteristics, right? How is it? It is something like this. Now, this is your VCE and this is your IC. Similarly, can also be for ID, and this can also for VDS. So for both for MOSFETs and BJTs, you have a similar kind of a output characteristic, right? Now, what we can say is, in this region, it acts as a current source, right? So as VDS changes across a transistor or VCE changes across a BJT, right, the collector current or the drain current remain constant. So this can be implemented, or in other words, in many cases it is implemented as a transistor. Okay. This is the way it is implemented in many cases. Okay. So this is given a some kind of a bias voltage, okay, and or in the case of BJTs, in order to kind of make it more stable, you might put some kind of an RE, and you give a certain bias voltage. Okay. So whatever it is, or even without this, you can basically give. Now, how to bias this? How to give this bias voltage? That is the question. Okay. So I want a precise amount of current. Let's say I need a 1 milliamp of current. Okay. Now, many times, in fact, if you look at the op amp internal circuits, you will see these kinds of circuits. And also, in many times, what happens is you will have one good reference which is generating a very precise current reference. Okay. Something like what you did in lab last time. You put a op amp or something like that, and you generate a very precise amount of current. Okay. and that current gets copied over to multiple circuits which might be in your board or your breadboard or whatever. Okay. So basically the way in which it is typically done is you have one reference current which is given. Okay. So you do a lot of things to make sure that it is a very stable across temperature and other things, right? And then you need to copy this current. Okay. So you need to copy it to multiple instances in your circuit where you need this current source. Let's say you have 5 current sources which are needed in your circuit. So you need to have a way of copying. Now, when I say copy, basically what do you need to do in order to replicate this current, or take a, let's say you want to have a ratio of these currents, right? What you need to do is you need a suitable VB. Okay, the way in which it is copied is basically you put something here which does this current to VBE translation. Okay, and this VBE is given to multiple blocks that need it. Okay, so let's say this was the one that we talked about. So then what happens for the same VBE? You'll have the same amount of current. So nominally the same amount of current will be provided here. Sometimes, of course, you'll end up with a little bit of mismatch because two transistors will not be identical. So a little bit of difference in that IS will happen, and therefore you will have a little bit of mismatch. But then if all things are in the same thermal region, then even if there is a drift in the temperature, all these things the VBE will start tracking. Okay, so this is what is called as a current mirror. Okay, basically you are mirroring the current. Okay, so you have a reference current which is done very nicely, and then you make copies of that current wherever you need it. Okay, now what we need to find out is how do you implement this block? How do you implement the block which translates this reference current to a reference VBE? Okay, that is what is needed. Okay, now the way that is done very easily by means of a diode connected transistor. Okay, so you have IREF, you put it through a BJT, and you diode connected it. Now what happens? This VBE automatically is adjusted such that you get it supports this IREF. Now if you take this and give it to another transistor, nominally you will say that I naught is equal to I ref. Okay, and the output impedance of this current source is nothing but the output impedance of your BJT, which is R naught. Okay, and if it is fairly high, then it is pretty good. Okay, now suppose you want 2 times I ref, all you need to do is take the same line, connect it to 2 identical BJTs, and short their collectors. Now this I1 is equal to 2 times I ref. Okay, so you can make copies of this current and also scaled copies of these currents. Okay, now this is what is called as current mirror, and this is the way biasing is done, especially when you talk about on-chip circuits. So if you open the circuit of let's say one of the op amps, you will see a lot of quite a few transistors which are diode connected like this. Basically what it is doing is it is mirroring the current. This is called as a simple current mirror. Okay. There are of course more advanced topologies, more advanced ways of mirroring currents and generating current sources. That's of course beyond the scope of this class, but this is one way of copying currents. Okay. Now the same thing can be done using MOSFETs. So MOSFET current mirrors are also there. Now some of you might look at this circuit and say, okay, there is a small problem. Okay, so if there is this IREF which is coming in, right, there is a little bit of IB1 which goes in here, and there is a little IB2 which is going to go in here, and IB3 here, and IB4 here, right? So which basically means that the actual current which is going into this diode, let's say ID is nothing but Iref minus sum of all the IBs, correct? Let's say IBI. Okay, so this is a problem in BJT circuits. So there are some techniques where you kind of put some beta boosters and things like that. That is, put an additional circuit to provide only the base current and so on. So all that is there. Okay, but nominally this is one problem which is there. So you cannot keep adding a lot of transistors. Okay, so if you are having 1 milliamp reference current and then you are only having, let's say, 2-3 transistors, you can basically ignore the base current, and if your beta is high. But if you are connecting to a large number of transistors, you will have to think about it. Okay, there are other techniques which you need to use. Okay, now in the case of a MOSFET current mirror, the same concept is existing. Okay, so you take some IREF, okay, and you put it through a MOSFET and you diode connect it. Now here in a MOSFET, you don't have any physical diode being generated just because you do this gate and drain connection. It is just the nomenclature which is stuck on from the BJT days. Okay, so unlike a BJT where a physical diode is actually formed, okay, here you do not have, of course, the parasitic diodes are there, but I mean they don't come into the picture of when the MOSFET is in operation. Okay, so but this is just the nomenclature. Okay, so don't think that the diode is formed. But here again, what happens is the VGS of this transistor is such that it can support IREF current. Okay, or in other words, VGS can be written as the threshold voltage plus root of 2 times ID divided by mu n Cox by W over. Okay, so it will automatically generate this gate to source voltage, and this can be mirrored to any number of transistors. Okay, and here you don't, here IG is 0, and therefore the problem of some amount of current getting diverted from the actual reference, that problem does not exist. Okay, it's a very neat solution. IG is 0, and therefore you can just basically mirror it to any number of transistors that you want. Okay, there is no limit on it. Okay, and this is what is called as a current mirror circuit using MOSFETs. Okay, now an interesting property of these diode connected transistors, okay, is this. Now if you look at this transistor, okay, VDS is equal to VGS, correct? Because the drain and gate are connected, VDS is equal to VGS, which means that it is always greater than, not even equal, it is always greater than VGS minus VTH. Okay, which means that a diode connected transistor is always in saturation. Okay, this diode connected transistor is always in saturation region. Okay, similarly you can say that a diode connected BJT, of course the VCE is equal to VBE, which is nominally around 0.7, and therefore it is always in the forward active mode. Okay, so that is another thing that you can see, but more importantly in MOSFETs it is always in saturation. Okay, all right, so let us try to solve one more problem. Okay, let's say you have a 10 mega ohm resistor, two 10 mega ohm resistors.
Sir,
Yeah,
sir, I have a doubt.
yeah,
Can we go to previous page?
yeah. This one?
Yes, sir. Sir, in the middle MOSFET, is that line connected to body or it is
No. It is
mirrored?
basically it is the same gate only. Okay, not the body.
Okay, okay.
Yeah. This is a way of drawing circuits, like which is conventionally, understood to be that the same gate is connected to all these other gates. Same connection is given to all the other gates. Okay. Yeah.
Okay, sir. Thank you.
Yeah. Sometimes it can be confusing, especially when you look at it for the first time. But then this is the typical convention. Okay. So here RD is given as 6 kilo ohm, RS is also 6 kilo ohm, okay, and basically determine all node voltages and branch currents. Okay, the threshold voltage is given as 1 volt. Kn dash into W by L is given by 1 milliamp per volt squared. Lambda can be taken as 0. Okay, as I mentioned, Kn dash is nothing but mu and Cox. Okay, so that into W by L, the whole thing is given by 1 milliamp per volt squared. Okay, now since so here, solving these circuits are a little easier than BJT because Ig is basically 0. Okay, so it means that this particular node, let's call it VA. VA is nothing but 5 volt, correct? It's a voltage divider, very straightforward. VA is 5 volt, and the current through the transistors, let's call it I1. Current through this resistors is also simple. So that is 10 volt divided by 20 meg, right? So that is 0.5 microamps, correct? Now we need to know what is the current that is flowing through the MOSFET. That is something that we don't know. Okay. Now what is this? What is the gate to source voltage here? So that also is something that we don't know. So we need to solve it. Okay. So this voltage is 5 volt. Okay. This is 5 volt now, and what we can write here is ID equation can be written as 1 milliamp per volt squared into VGS minus 1 volt the whole square. We don't know VGS and we also don't know ID. Okay. Now VGS can be written as what? VGS can be written as 5 minus VGS is equal to, this is the voltage, okay, is nothing but ID times RS. Okay, is it clear? So you have VGS here, okay. So the voltage across the resistor is nothing but 5 minus VGS, right? 5 volt minus VGS, and that is equal to the IR drop, which is ID times 6 kilo ohm. Now you substitute this in this one, okay. You can substitute for either ID or you can substitute for VGS. So let us say you substitute for VGS, okay, and find ID. So it will be a quadratic equation. So you will get two possible values for ID. So can you solve it and tell me what are the two possible values of ID? Basically, you can write VGS to be 5 minus ID times 6K. You substitute this here.
Sir, shouldn't it be 1 by 2? And
Yeah,
ID
yeah,
equation.
you're right. Yeah, mu and Cox by 2. You're right.
So here also we have assumed saturation region and then we are working the
Correct.
backtracking
So,
actually.
yes. So again, that's another point that I missed telling. So here what you do is you assume saturation region, okay, and then you evaluate it and then you finally verify if your assumption is true. Okay, there will be some problems in the exercise or in the textbook where you will see that if you will take this assumption, you will work it out and you will get either some very absurd numbers or unrealistic numbers. uh, things like that, and then you know that basically your assumption was wrong. For example, if you end up with a value of ID which is complex, then you know that your answer is wrong, right? Because we are talking about DC circuits, and if you have a complex number as your current, then it means that you have either made mistake somewhere or your assumption that it is in the saturation region is wrong. Then you'll have to go and assume that it is in the triode region and use that equation, and that time it will be correct. So I hope all of you are working it out. So please do work out the problems. So has anyone found the answer? What are the two possible values of ID? So anyone has got an answer? 2 volt, no.
So 0.5 milliampere.
Okay. And
0.8 milliampere. 8.
correct. So it is either you get two answers, 0.5 milliampere and 0.89 milliampere. Okay. So now it is important to figure out which of these two answers is correct. Okay. So you solved the quadratic equation and you got these two, but in this circuit, in this context, which of the two actually makes sense, right? So if you substitute 0.89 milliampere, okay, let's just do a sanity check. Okay. So if you take 0.98 milliampere, what is Vs? Vs is 0.89 into 6. How much are you getting? 5.3 something,
Yes, sir.
right? Around 5.3 volt or something like that, right? Whereas if you take Vs here, it is 3 volt, correct? Now, if you take this Vs, the source voltage to be 3 volt, then Vgs is equal to 2 volt. Oh, okay. I'm sorry. I think whoever had put the thing, that is correct. Your Vgs is 2 volt. Ujjwal, you're right actually. Yeah. So Vgs is, yeah. So here what happens? 0.5 milliampere. If you take, you have Vs of 3 volt and you get a Vgs of 2 volt. Whereas if you take Vs of 5.3, here Vs is greater than the gate voltage. Okay, so this is not a correct solution. This is a wrong solution. This is the right solution. So this gives us a VGS of 2 volt. Okay. Of course, I think Ujjwal, you would have substituted for VGS and solved it directly or something like that.
Yes, sir.
Okay. All right. Okay, so let's move on. So this is the problem. I mean, so the okay, good. Yeah. So you can do either ways, and you can solve the thing. So you when especially in these MOSFET problems, you might get two solutions to the equation, but you'll have to look at the circuit and figure out which one is valid and which one is invalid. Okay. In this case, the second solution is invalid. Only the first solution is valid. Okay. All right. Fine. So let us proceed. Now, I want to talk about what is called as voltage transfer characteristics. Okay. So basically, this is a fancy name for understanding what happens when if you take a simple, let's say, common emitter type, sorry, common source type circuit. Okay, let's say this is V in and this is V out. You have a certain RD. Okay, and in the meantime, I also want to take, let's say, RC. I don't know if I did it for BJT. Let's say this is V in and V out. Okay. Okay. So what we are going to do is, this is a large signal analysis. Okay, this is also called as large signal in the sense that you are sweeping V in from, let's say, 0 to the maximum, either VCC or VDD. Okay, and you want to look at the output. So what happens? Let's first look at the BJT case. Okay, I am using the same color so that it is clear. Let's say this is VCC. So when V in is 0, what will be your output? When V in is 0 for a BJT for this particular circuit, right? What will be the output voltage? Maybe you can unmute and answer.
VCC or
It will be VCC, correct? Because when V in is 0, IC is 0, correct? So if IC is 0, V out, which is written as VCC minus IC times RC. Okay. So if IC is 0, V out becomes equal to VCC. Alright. If there is no current flow across the resistor, then the voltage drop across the resistor is 0, and therefore both the nodes will be at the same potential. Okay. So in this case, it is going to be at VCC. Right. Now you keep increasing Vn, right, and you hit close to, let's say, the cut-in voltage. What happens? Current starts flowing, and then what will happen to the voltage?
start dropping.
It will start dropping. Correct. So in the initial region where the current is still 0, you still are at VCC, and slowly you start dropping, and then as it starts conducting, it will very rapidly drop. Right. Now, what happens when it goes to, let's say, very close to, when Vn is close to VCC?
Saturation or
Correct. So it will basically, so in this mode, this is basically, it is transistor is off. This is the forward active mode, right? And then it goes to,
goes down to 0.
yeah, it will not go to 0 because there is a current flow. It will go to VCE sat. Is it clear? Because as the current reduces, what happens is, as the current increases and as it goes into the saturation region, the BJT saturation region, you will basically get a VCE equal to VCE sat. Okay, it will not go down to 0. This is the voltage transfer characteristics of a BJT. So let me do that for, let's say, let me draw it again. Let's say this is V in, this is V out. Now this is for MOSFETs. So for the MOSFET, when Vin is 0, so let's say this is VDD. Okay. Now when Vin is 0, what will be the output?
VDD.
It will be VDD. Okay. So here again, V out is given by VDD minus ID times RD. So for Vin equal to 0, ID is 0 and therefore no current flow through the resistor. Both terminals are in the same potential. So this is at VDD. Okay. And same thing till threshold voltage, it will remain there and then it will start dropping, right? And then what will happen when you know Vin goes to VDD?
It will enter saturation mode.
No. So here it is in the okay. So here it is in cutoff. So here it is in saturation, right? This is the saturation where Vin is small and VD. So here in this region, VDS is greater than VGS minus VTH because Vin is small and you have a very large VDS. Okay. Of course, as you go somewhere here, right? So as you go somewhere, let me draw it like this. Somewhere here, what happens? Your VDD minus IDRD becomes a lower thing. Now here it reaches the triode region. Okay. And then finally what happens? As you keep increasing, the current keeps increasing. And then you will reach a point where you can reach absolute zero. Okay. All right. So for the circuit to work as an amplifier, you basically want it to, for a BJT, you want to be in the slope region. Okay. Oops. Okay. This is where the circuit acts as an amplifier. Okay. You can see that V in to V out, there is a pretty good slope here, right? And this is where a small change in V in, right, will result in a larger change in V out. This is where it acts as an amplifier. Okay. Same way, you want it to be in the saturation region, and this is where a small change in V in will give a larger change in V out. Okay. So this is the region where you want your transistor to be in in order for it to act as an amplifier. Okay. But whereas when you talk about digital circuits, okay, I'm sure all of you are familiar with an inverter, right? What is an inverter? You give an digital 1, the output is digital 0, okay? And if your logic 1 and logic 0 are, let's say, represented as, let's say, two voltage levels, let's say VCC and ground or VDD and ground, okay? So what happens is, in the digital world, you are more interested in being either here or here, right? Same way in the digital world, you want to be here or you want to be here. Okay. So this is where digital circuits work, and the yellow region is where the analog circuits work. Okay. So that is an important distinction that you must know. Another thing that we see here is when there is current flow, okay, for a BJT, VCE never becomes 0 when IC is greater than 0. Alright. So which means that there will be always some current flow happening. Okay. So this is something that you will learn in more detail in the digital circuits course in the next semester. Okay. So here what happens is when there is current flow, VCE will always be greater than 0. Okay. But whereas here in MOSFETs, you will get very clean, you get a clean VDD and clean ground. Okay. And this is a very big advantage. In fact, I think when you look at digital circuits, you will look at it in more detail. You will see that the static power dissipation in a digital MOS circuit, okay, CMOS circuits is 0, whereas the static power consumption, static meaning it is either at the logic is either at 1 or it is at 0. Okay, in such a case, the static power consumption, that is when it is not toggling, when it is not switching, let's say you have a 1 or a 0 and it is constant, there is still current flow happening in a BJT based logic circuit. Whereas in a MOSFET based circuit, you will not have any current consumption there, and you will get very clean zeros and also clean VDDs. Okay, and that is the reason why MOSFETs have taken over the entire digital world, and pretty much, I should say, almost all digital circuits, processors in today's world are made out of MOSFETs. Okay, all right. So it's almost time. Now let me just quickly move over to so just like how you have, let's say, a common emitter amplifier, let me just write it as CE amplifier in BJTs, and then you have a common base amplifier, you have common collector amplifier, which is also called as emitter follower, right? Similarly, in MOSFETs, okay, this is called as a common source amplifier. Okay, common source amplifier is where you have a resistor, something like this, okay, and this becomes a common gate amplifier, and then this becomes a common drain amplifier. Similar to emitter follower, this is called as source follower. Okay, so what we will do in the next one, I think I can cover it in one class. Hopefully, we will go through all these three topologies, and we can quickly cover it. Okay, and before closing today's class, let me just give the small signal equivalent circuit model. Okay, so same hybrid pi model we can use. Okay, so it is very similar. So basically you have GM times VGS, small VGS, and you have R0. Now this is the drain, this is the source, and this is your gate. Now here what happens is there is no resistor between the gate and the source because there is no current flow. Okay, so basically the gate and source are fully isolated. It is an open circuit. There is nothing between gate and source. You only develop a certain voltage. Okay, it's an open circuit basically, and this is the small signal equivalent circuit of a MOSFET. Okay, and there are cases your body effect comes into picture. Now, if your body effect is coming into the picture, the way it is drawn is nothing but GM-VGS, and in parallel you have one more current source called as GMB-VBS. Okay, so I will probably talk about. Okay, so this is the thing with body effect. This is your gate, this is your source, this is your drain. So now that we have developed a small signal model, you can basically use the same techniques that we used for our BJT circuits, and you can derive the small signal parameters like gain and so on. Okay, and GMB basically maybe I will cover it next time, or maybe it is not so important for in this course, but I'll just give you the idea. So as I mentioned, ID is mu and Cox by 2 W over L, VGS minus VTH the whole square. Now this VTH can be written as VTH naught plus gamma times root of some 2 pi f plus VSB minus root of 2 pi f. Okay, so this is your the whole square, right? VGS minus VTH the whole square. Now what you can do is you can find out dou ID by dou VBS. Okay, and this is defined as GMB. Okay, now usually this is given as a small signal parameter so that you don't have to do this very tedious differentiation and so on. Okay, but this is just to give you an idea from where this GMB is coming. Okay, it is basically to say that the current not only depends on the VGS, it also depends on the VBS because the threshold voltage is now getting modified. Okay, and it's only in those circuits where the body effect comes into picture, you need to take this into account, but for most of the circuits we don't do that in this course. Okay, so with this I'll complete my lecture today. Since there is only one more week of lectures and I want to cover a little more portion, I will record some lectures and I will upload them. Okay, and I'll let you know, so please do go through them. Probably this common source, common gate, common drain, I'll put it as one lecture. You can go through it. So that will be included in the thing. Just because we are kind of running out of time, I'm doing that. And probably next week we will look at some Darlington pairs, multi-stage amplifier, power amplifiers, tuned amplifiers. So that is what I wanted to cover, and with that my portion of this course will be over. Okay, so maybe 2-3 lectures I might just post it as videos, purely because of lack of time. So please do go through it, and because these are important concepts, and I'm pretty sure you'll be able to do it. Okay, all right. Now regarding lab, tomorrow we'll have one lab session, and Thursday again we'll have another lab session. Now these two are your final lab sessions. Okay, and the following week we are going to have the lab exam. Okay, the way in which we are going to do the lab exam is that each student will have about 1.5 hours. Okay, we'll probably start by 1:30 to 3, and 3 to 4:30 will be 2 slots each day. So Monday is a holiday, so we will not have any exam that day, or classes for that matter. So Tuesday, Wednesday, and Thursday. So basically we have 3 afternoons, and each afternoon we have 2 slots. So that means 6 slots. Okay. So we'll each slot we'll try to accommodate around 10 or 11 students, and I hope so. What is the strength? Is it 65 or 66?
65.
55.
65. Okay. So we'll probably have 11 students per slot. So the way in which we are going to do it is like this. Okay. So each student gets about 1.5 hours, and you will be given we'll have a set of questions, and we'll do some random number generation or something like that to randomly assign questions to the students. Let's say you are a student who is coming in at the 1:30 batch. So we will give you a question, which will basically be from the experiments that you have already done in the lab. Of course, definitely the numbers will be changed. And so now you need to do a pen and paper design, okay, and also simulate it in LT-Spice. Okay, do the simulation in LT-Spice and put the results together and upload the document within 1 hour in Moodle. Okay. Now once you do that, we have maybe around 3 staff members in the lab. So they will go one by one, and they will implement your circuit, and they will give you the measured result, which you need to plot and submit a complete report in another link that I will provide in the Moodle page. So that will be your lab record. Okay, I mean your lab exam report. So basically each of you will have to do it individually. So all the reports that you have already submitted, okay, they will be there for your reference. The final grading will take into account your performance in the lab exam, and also the reports that you are submitting for the lab assignments. Okay, and also the other project that I was talking about, which you need to, where you need to design a PCB. Okay, it can be a small PCB, just a small circuit, but you need to be able to explain it, do a schematic design and a layout design, and show that. So for that you have time till probably the end of next month. Okay. So when are your exams getting over?
18 December.
15th December. Okay. All right. So basically before 23rd, or let's say you have, before 20th December, let's have your project marks also done. Okay. So you have time for your project till 20th December. Okay. And